Hi folks, and welcome back for the final video in section 1.5 about continuity. In this section, we're going to meet something that's called the intermediate value theorem. So in math, a theorem is just a fact, and if it's important enough to have a name, it's really important. So we're going to just spend this video meeting this thing and learning how you use it and when you use it. So what the intermediate value theorem does is it helps us know ahead of time if a function has a solution or not without actually having to calculate that solution. You may have met before, you write down some equation and you want to know if you can solve it when it equals 0. If I just make one up, something like x to the 4th minus 3x squared plus 5x plus 1, I want to solve that equal to 0. That's a hard equation to solve. And I don't want to go through all that work just to find out that there weren't any solutions to start off with. So what the intermediate value theorem does is it gives us kind of an easier way to check and see if we expect there to be a solution or not. And that can guide what we go do from there. So here's what the intermediate value theorem says. In math speak first, and then I'll write it in a little differently. If I have a continuous function and a closed interval, has to be a closed interval and not an open interval. Then it says for any k strictly between f of a and f of b. What on earth are they talking about there? Well, let's draw a picture. Here's my coordinate plane. And let's see what kind of setup we've got so far. So I have a closed interval from a to b, and I have a continuous function. So maybe f starts right here, and it wiggles around, and it ends up back right here. And so what that means is that we've got two corresponding y values over here. We've got f of a is the higher one, and we've got f of b, because those are just lining up with their points. Okay? So then this intermediate value theorem says that for any k between f of a and f of b. So if I put k somewhere in between, it doesn't have to be right in the middle, it could be anywhere at all as long as it's in between, then there exists at least one c somewhere in between a and b. Now c is an x value, so there's at least one x value in between a and b so that f of c equals k. So what that means is that if I follow this k line over to my graph, there's got to be some point on that graph whose y value is k. And that means that there's got to be some x value down here that corresponds to that point. Alright, so another way of saying that is just as long as f is continuous, and I look at the two y values, f of a and f of b, then the graph has to pass through every possible y value in between f of a and f of b. It can't skip any, because if it skipped one, then it wouldn't be continuous. So as long as it's continuous, it has to go through all the y values in between this y value and this y value in order to get from one point to the other. Okay? So we'll see how to use this in just a minute. I do want to point out that continuous is absolutely essential here, because if I showed you one of those graphs where it was not continuous, let's say I've got one of the ones that goes like that, then I could find a k right here in the middle where there's no points on the graph there. So it has to be continuous. That's important. Now, it turns out that most of the time this intermediate value theorem gets used when k equals 0. Okay? And what it says then, if k equals 0, let me adjust my graph here. Okay, he's not up here anymore. If k equals 0, that means that my k is right here. Then if I have one point of my graph below k and another point of my graph above it, let's say this one's at A and this one's at B, then somewhere in between A and B, f absolutely must have a root or a 0. It has to cross the x-axis somewhere in between. And you can see it from the picture. If I start down here at f of A, and I've got to get to f of B, and I can't pick my pencil up, well, somewhere I have to cross the axis. I can't possibly do it any other way. And so this is the 0 that they're talking about. As long as I know that f of A and f of B have opposite signs, one's negative, one's positive, then there's got to be a 0 somewhere in the middle. So let's see an actual example. I've got a polynomial function, x to the third minus 3x plus 1. We know polynomials are continuous. So the question is there some c in the interval 0, 2 whose y value equals 2? I'm not asking you to find the c. I'm only asking you, is there one? So if I wanted to check this out, then I've got my closed interval. They gave it to me, 0 and 2. So in order to go anywhere with the intermediate value theorem, I need to know what the y values are for 0 and 2. So that just means I got to plug in some numbers. So when I plug in 0, I get 0 to the third minus 3 times 0 plus 1, so that's just 1. And when I plug in 2, I get 2 to the third minus 3 times 2 plus 1. And that comes out to be 3. Okay? So in this particular problem, my x's are going from 0 to 2, and my y's are going from 1 to 3. So if I edit my graph a little bit over here, so k is no longer right there. And actually A is now at 0. So we've got, here's 0, and then here's 2. And we decided that f of 0 was 1, and f of 2 was 3. Now the k is the number they're asking about. So if this is 1 and this is 3, then here's k because that's 2. So if I'm drawing this graph and I'm starting at a point down here at 1 and I want to end at this point up at 3, do I have to cross 2 somewhere? Well, yeah, I do, because 2 is in between 1 and 3. Okay, so we can say that, yes, there is a point a c where f of c equals 2 by, and I'm going to abbreviate, intermediate value theorem. Okay, now I have absolutely no idea what this c number is. It could be 0.0001, or it could be 1.99999, or it could be right here in the middle at 1. All I know is it's somewhere in between 0 and 2. But at least now I know that there is a 0 in between, or sorry, there is a point where f of c equals 2 in between these two. So if I go looking for it, I'm not wasting my time looking for something that's not there. All right, now in this class, we are not at all interested in finding the point. I just want you to see that one of the things that continuity helps us do is to know ahead of time, without doing a lot of hard calculations, whether or not we can find these c's, right? All we did was we plugged in 0 and we plugged in 2. And we said, okay, so if the x's go from 0 to 2, then the y's are going from 1 to 3. And since 2 is in between 1 and 3, then I have to cross 2. So yes, there's some point whose y value is 2. I don't know where it is, but I know that there is one. All right, so let's try another one. So this time, I want to know if we have a 0. So 0 is playing the role of k. And I want to know about between -1 and 2. So this is going to be a, and this is going to be b. So I need to find f of -1. So that's going to be 3 times -1 to the third plus 3 times -1 squared minus 6 times -1. And when I put all of that together, I get 6 in my calculator. And I need to know what's the y value that goes with 2, so I'm going to plug in 2. So 3 times 2 to the third is 3 times 2 squared minus 6 times 2. And I put all of that in my calculator, and I get 24. All right, so now what I've got is I've got a situation where my x's are going from -1 to 2, but my y's are going from 6 to 24. Any reason to think that there should be a point where y equals 0 in between 6 and 24? Well, no. So we can say no, because 0 is not between 6 and 24. Now, if the picture is helpful to you, then here's our graph. I've got -1 over here, and I've got 2 over here. So what we just figured out was that -1 had a y value of 6, and my graph is obviously not to scale, but 2 has a y value way up here that's 24. So if I'm trying to get from this point to this point, there's no reason to guarantee that I had to cross the x-axis down here where y is 0. Now, just to be real clear about something, it is possible that this function does cross the x-axis. It could conceivably, instead of going straight from one point to the other, it could conceivably go down and back up. But it doesn't have to, and that's the key point here. The intermediate value theorem only tells us what the function has to do. And in this case, it doesn't have to go down to the x-axis. It could, but it doesn't have to. It only has to go through the numbers in between 6 and 24. And it can't avoid any of them. So for this one, we say no. All right, same function, but new interval and new number. So let's try this one. And this will pretty much wrap us up for this video. So I've got the same function I had just a minute ago, and I have a different interval. I have -1 to 3. So let's see, we need to check out f of -1, and f of -1 is going to be -1 to the third, 3 times -1 squared, minus 6 times negative 1. And that comes out to be 8. And I need to find f of 3 because that's my second x value. So 3 to the third is 3 times 3 squared minus 6 times 3. And when I do all of that, I come up with 36. All right. So if my x's are going from negative 1 to 3, my y's go from 8 to 36. Is there any reason to believe that we had to cross a point whose y value is negative 1? Well, same deal. No, because negative 1 is not between 8 and 36. Okay. So I want to point out that changing the x values absolutely can change the answer here. So be sure you pay attention to the x values that are given to you. And then the end of the day, the question is just, is the y value that they're asking about in between the two y values that we get? If it is, then we can say, yes, there has to be a point with that y value. And if it's not, then we have to say, no, there doesn't have to be a point. There might be one, but there doesn't have to be one. So that'll wrap us up for section 1.5. We'll do a little bit more in class dealing with particular continuous functions and what they look like and how you know where they're continuous. But this will wrap up this section, and then there's only one more section in chapter 1 before our first test.